Standard cosmology operates on a deep, almost invisible premise. The universe as a whole possesses exactly zero angular momentum. In the equations that model our cosmos, global rotation is set to a strict zero. That baseline is baked directly into the Friedmann-Lemaitre-Robertson-Walker metric, or FLRW. This mathematical framework demands strict homogeneity and isotropy, meaning the universe looks the same in every direction, everywhere. Any net rotation would violate these conditions, so it is mathematically removed before the analysis even begins. Looking through the hexagonal mirrors of the James Webb Space Telescope, we find observational data that challenges that non-rotating baseline. Deep field surveys reveal an asymmetry in galaxy spin directions, with a slight but persistent excess of galaxies rotating in a specific chiral direction. Parallel to the JWST data, the Planck Legacy 2018 analysis of the cosmic microwave background introduces a second major friction point. The data actively prefers a closed universe topology over a flat geometry at greater than a 99% confidence level. These accumulating observations suggest the initial premise of a non-rotating universe may be masking the actual rotational dynamics of the cosmos. The exact absence of cosmic rotation is not a derived physical law. General relativity itself accommodates a rotating universe perfectly well. The zero rotation state is instead manually imposed by our choice of early universe models. Standard treatments rely on simple, single scalar field inflation models. By design, these specific models cannot source primordial vector perturbations, effectively forcing initial angular momentum to zero. This chart models the probability of random vector cancellations across multiple independent spatial grids. To achieve a net angular momentum of exactly zero across the entire cosmos requires coordinated cancellations at every scale. Without a specific dynamical mechanism to enforce it, this demands a level of statistical fine-tuning that makes an exactly zero-spin universe highly improbable. Foundational logic, quantum field theory, and strict conservation laws suggest an alternative. The physical and mathematical conditions required to support a structured universe mandate that the universe must inherently rotate. This presents a distinct paradox. If physical laws dictate that the universe must possess angular momentum, we have to explain why our oldest light, the cosmic microwave background, appears perfectly isotropic and devoid of a preferred axis. If we observe a completely uniform, featureless void, we are looking at a system that draws no distinctions. To exist in an operationally meaningful sense, to possess structure, distinct objects, or observers capable of measuring them, a system must exhibit inhomogeneity. Fluctuation and density variations are the minimum requirements for a measurable reality. We can contrast that with absolute rest. A state of true rest, devoid of net flux or force, is the thermodynamic equivalent of maximum entropy and perfect equilibrium. Equilibrium dictates perfect homogeneity. If existence strictly requires inhomogeneity and absolute rest strictly requires homogeneity, the two states are mutually exclusive. Any universe capable of supporting observers excludes a state of absolute rest. It must contain motion. As the universe expands, that basic motion evolves into rotation. Physicists like James Peebles established classical tidal torque theory, demonstrating how physical structures acquire spin. When an inhomogeneous mass distribution collapses, misaligned inertia and tidal shear tensors inevitably cross-couple, generating angular momentum. This diagram visualizes a spectator complex scalar field with internal U1 symmetry. During inflation's extreme expansion, quantum fluctuations stretch, creating uneven spatial gradients. As the universe cools, these gradients re-enter the causal horizon, converting into bulk momentum flow and sourcing genuine spatial angular momentum. Classical tidal forces acting on early mass distributions and quantum fields operating during inflation yield the same outcome. An inhomogeneous universe naturally generates a non-zero global angular momentum. A common theoretical objection arises here. General relativity struggles to define a globally conserved angular momentum for the entire expanding spacetime because it lacks a global time-like killing vector. The Chen-Wang-Yao formalism resolves this by embedding a space-like 2 surface into Minkowski space, defining conserved quantities at a quasi-local scale. Within this boundary, total angular momentum remains strictly conserved. As the universe expands, angular velocity must drop proportionally to the scale factor squared. When we extrapolate this expansion backward, the rotation rate increases. Tracing this curve toward the beginning of time eventually hits a physical ceiling, the speed of light. Because no physical rotation can exceed the speed of light, the primordial state is naturally capped at c. This intersection between conservation laws and relativity provides a definitive starting point, one that predicts a remarkably small, but mathematically non-zero, rotation rate in the present day. General relativity does not erase primordial rotation. It preserves the total angular momentum entirely, continuously diluting angular velocity across 13.8 billion years of expansion. This all-sky map of cosmic microwave background temperature anisotropies presents the final hurdle. The Saade bound places a severe upper limit on cosmic vorticity. The constraint is typically cited to argue the universe does not rotate. However, the Saade limit of omega less than 10 to the negative 9th radians per year strictly rules out models rotating on a single axis. A single-axis rotation creates enormous CMB temperature distortions, which we don't see. The solution is a closed S3 or RP3 manifold supporting Clifford isoclinic rotations, simultaneous rotation in two orthogonal planes. By counter-aligning these rotations, net angular momentum cancels observationally, leaving a distortion-free CMB. The isotropic CMB does not disprove a rotating universe. It acts as a strict topological selector, demanding that the universe exist as a closed, counter-rotating manifold. The mathematics of Clifford rotation align with independent observations. The Planck Legacy 2018 analysis, which found a greater than 99% confidence in a closed universe, describes exactly the RP3 topology required by this rotational model. This residual rotation also helps address the Hubble tension, the persistent discrepancy between the expansion rate we measure in the early universe versus what we see in nearby galaxies. By factoring in this rotational component, the gap between these two fundamental measurements narrows significantly. Dropping the arbitrary assumption of zero angular momentum resolves independent, major cosmological anomalies. It does so without requiring the invention of new particles, dark fluids, or modified gravity. Embracing a rotating universe requires zero new physics. It relies entirely on applying the established conservation laws of general relativity and quantum mechanics to the cosmological background. The apparent stillness of the cosmos is an illusion. It is a product of exact topological symmetry, balancing out opposing momentum, stretched by deep time expansion until the velocity is nearly imperceptible. The lambda CDM framework has inherited the assumption of zero angular momentum from the simplest mathematical models of inflation. It is time to challenge that framework to explicitly justify a perfectly still cosmos, given the physical improbability of such a state. The immediate priority for cosmology is to program CMB Boltzmann code calculations to explicitly test for the signatures of Clifford counter-rotation on an RP3 topology. Rotation is a logical necessity, rooted in the physical conditions of existence itself. A universe that exists must rotate.